everyone, today we are finally going to implement the UNet model. So the original UNet model was proposed for biomedical image segmentation, and it still is a very capable segmentation model, image segmentation. But our main purpose is actually to implement the UNet for a future diffusion implementation that we'll be doing, because again, the UNet is used in that architecture as well. So what I want to do today is explore the UNet for image segmentation specifically, because again, that's kind of the original purpose of this model. But then when we go to do diffusion in one of our future videos, we'll copy paste a lot of this code over. There's a couple of extra things we're going to have to add in for the diffusion model. We'll talk about that when we get there. But for today, we're going to implement this UNet, see what it looks like, and we'll train it on the popular ADE20K dataset. So we'll also write a data loader, a training script, all that sort of stuff. And so first of all, what is the difference between a UNet and an autoencoder is a typical question. And so a UNet, as you see here, you start with some input and you kind of compress down, and then you kind of decompress and you go back up and that's it, right? So you compress down to some bottleneck and you decompress back to your original image space. Well, that sounds a lot like an autoencoder, right? You take some data, you compress it down to your bottleneck, and then you decompress. The main difference between an autoencoder and a UNet is that in the autoencoder, there's no dependency between the encoder and decoder. They're kind of two separate things. In the UNet, we take outputs of every stage of our encoder and merge them in some way. We do a residual connection essentially. So if you don't know what ResNet is, you can go ahead and take a look at that. But we do some sort of a residual connection connecting our inputs to kind of the upsample blocks, right? So we take every output of each block in our encoder, and then we just concatenate them on or add them on, and we kind of decode that way. The main reason you'd want this is because when you encode and decode an image, you end up losing a lot of potentially fine-grained detail or kind of general features that were available at every single stage. So this is kind of like reminding the neural network of what did it see at that stage in the encoder portion, right? That's the main idea. And there's two types of ways you can do this. You can do an additive connection. You can take the encoder block and add it to the decoder block, and you kind of get this, a combination of the two. Or you can do concatenation, where you just concatenate them together. In the ResNet architecture, which we implemented before, you go with the additive method, right? You add the residuals together. On the other hand, when in the UNet architecture, we do a concatenation. So that's what we'll be doing today. And so not much else to talk about. We're just going to go ahead and start implementing it and see what happens. So we're going to need you, and I'm going to keep you open for reference. And so in the UNet architecture, maybe it would be a little bit more helpful to do this. In the UNet architecture, what we need to do is define a couple different things. So let's go back here actually. We need to define a block. So each of these blocks, we're going to call them, basically it's a couple convolutions, right? So we're going to have a couple of convolutions in each of these blocks. We're going to call those residual blocks because inside each of these blocks, we're going to have a residual connection. So we'll see what that looks like. And we need the ability to downsample, right, as our image gets smaller and smaller, and we need to be able to upsample. Downsampling is no problem. When we downsample, we can just use a convolution with a stride of 2, right? So that'll automatically downsample by factors of 2. But when we upsample, we want to make sure we use some type of a method to upsample. We can either use interpolation or we can use transpose convolutions. And we're going to implement both of them today, and then we can put it all together. The UNet isn't a particularly hard architecture to implement. It's more just finicky to get things to align right, because you need to make sure your everything along your input, the encoder blocks, needs to match with everything along the decoder, otherwise it doesn't work out. So import torch.nn.functional as f, and I believe that's all we're going to need. So like I mentioned, the first step is we need to implement our residual block. So a residual block is just going to be a stack of 2 convolutions, and we're going to be using, so this won't be true to the original UNet implementation. It's going to be closer to the type of UNet you would see in diffusion, but a UNet's a UNet. It doesn't really make a difference for our potential use case right now. So we're going to go ahead and do class residual block, right? So residual block. And so this residual block, the goal of it will be, it's just going to be a stack of 2 convolutions, and we're going to connect them to each other with a residual connection. And this residual connection will be a additive connection rather than a concatenation one. So it's going to be in channels, out channels, and we're going to be using group normalization. Again, that's what's preferred in diffusion, so that's what we're going to be doing here. Group norm is very powerful and typically used for a lot of the different types of generative tasks, so we're going to implement it. It doesn't really matter. I'm sure there's better methods. Actually, UNet is not even close to state of the art for most segmentation tasks today, so but it is still the primary backbone for generative models, which is why we're mainly implementing this. So what we need is 2 convolutions, 2 group normalizations, and a potential residual connection. So let's go ahead and start it, and we'll see where the problems can be. We're going to do self.groupNorm1. It's going to be nn.groupNorm. If you don't remember what group normalization is, then now would probably be a good time to pull up a picture real quick. I always love this picture here. So let's go ahead and open it and show it. Here we go. I love this picture. So batch normalization normalizes along the batch, right? So along the batch dimension. Layer norm normalizes along the channel dimension. So each instance, so each sample is normalized individually. So that's the layer norm, but it happens across basically the entire sample. Instance norm does it along every single thing, like basically along the height and width dimension for every channel individually. And then group norm is kind of an interpolation between instance norm and layer norm, and group norm seems to be the most powerful for, it seems to be very good for generative tasks, which is again why we're implementing it. And so we have a group norm here. All we need to do in group norm is we need to provide it how many groups and the number of input channels, right? So this residual block is going to get some input channels, some output channels, and so we're going to have to just do a quick group norm num group. So how many groups do we want in the group normalization, and how many input channels are there? And so these are the 2 pieces of information that's going to need. And then our first convolution is going to be self.conv1. Conv1 is nn.conv2d, a 2D convolution with in channels, and then it's going to go to out channels. We're going to say it has a kernel size equals 3 and a padding equals same. So we want to make sure, and this is a super important part, there's 2 things we can change about an image, right? We can change the number of channels, or we can change the resolution of the image, right? So the height and width dimension. And so in these residual blocks, we're going to make sure we can update the number of channels. So if we have a, if we had some image that's, let's just go ahead and create some. So if name equals main, let's create a random tensor. So rand is torch.randn. And let's say we have a batch size of 4, 3 channels by 224 by 224. Let's say that's our image. Standard image shape for most image tasks that we care about. If this is our image space or image size that we want to work with, then we want to make sure a residual block, when it gets a tensor like this, it will only update the number of channels. We're going to not change the height and width. The reason we're doing this is I like to separate it out, otherwise it becomes too complicated. I like to change one thing at a time. Either we change the height and width of an image, or we change the number of channels in a single computation. And you'll see later on, we're also going to need to be able to update the height and width. That'll come a little bit later. And let's make these 256 by 256, right? So it's easy, divisible by 2, nice and easy. Or is a, a 2 to the power, it works out. Okay, good. So that's our group norm and conv1, and this will ensure that we don't update anything, and we only update the channel dimension, right? So the out channels. Now we're going to do self.groupNorm2 is nn. Again, group norm, and it's going to get how many groups we have. That's fine. And then we will provide it our out channels, right? Because this convolution projected from in channels to out channels, so the next group norm expects out channels number of stuff, right? So that's fair. And now we're going to have a second convolution, self.conv2 is nn.conv2d, and this is going to be in channels is going to be equal to just out channels, so it's going to be out channels to out channels. Again, kernel size equals 3, and padding equals same. So this will ensure that our image space does not change. And so what we can now do is def forward self x, and what we can do is, so we're going to say, let's do x is self.groupNorm group norm 1x. We're going to pass our data through a normalization. Then we're going to do f dot relu is pretty standard, so we're going to do a relu activation. So there we go. And then x is self dot con 1, right? 1 x. So just like that. So this is me passing my data through the first set of convolutions. After that, we're going to do again x is equal to self dot group norm 2 x. X is equal to f dot relu x. And again, x equals self dot con 2 x, just like that. So now I've taken my data, passed it through the second set of group normalization, relu, convolution, that sort of stuff. And now what we want to do is add the input x to the output of these convolutions. So what we're going to do is create a residual connection is equal to x. We're going to just store that variable ahead of time. And then once x is done, we're going to do x equals x plus residual connection. So again, if you don't know what residual connections are, go ahead and take a look at my ResNet video and it'll give you a little bit more context for what this is. But yeah, this is our residual connection to add our input to the output. Now again, going back to our figure, this is not these connections here. We're only looking at one block right now. So this is a operation that would happen inside a single block, and that's it. We'll do the concatenation stuff later. We're not there yet. We're just looking at a single block right now, a single block of convolutions. And we can return x. Now, this looks all well and good. And let's say we have 32 channels instead. Let's say we do block equals residual block. And let's say in channels is 32 and out channels is 32. Let's just keep it the same for now. If we take our block and pass in rand, this should be fine. So if we print here, let's do print x.shape, and everything else seems to be good. So we can run Python, not train, model.py. This should work out. A group norm num groups. Okay, I have to provide that as well. Let's just say we want 16 groups. Group norm num groups is 16 groups. It just has to be, the number of channels has to be divisible by the number of groups. And so that should be fine. 16 should work. And so we can see we have a 4 by 32 by 256 by 256. So no problem there, right? Everything worked out. Our input was added to the output. Our convolutions didn't cause any issues. So we're good. We're good to go. Except what if I make my out channels 64? Will this still work? It will not. It will throw an error saying the size of a tensor must match the size of the other tensor. And the problem is this. If we look at print x.shape before I do this connection, and if we print out our residual connection.shape, which was the original x, right? The original thing we passed in, just a copy of it, you'll see that, you will see that our residual connection, let's see, this 32, 64. Yes, so x.shape is 64 channels because it went through all these convolutions and the convolutions projected the original x, which had 32 channels, to 64 channels. So our x has 64 channels, but our residual connection, the original input x, only has 32 channels because that's what we started with. So I cannot add these two tensors together because they're not the same shape. So if they're not the same shape, we need to add an additional operation here called self.residual connection that only exists if the channel, so if the in channel and out channel are not the same. So in this case, it's 32 and 64. If they're not the same, then we'll have this error because we can't add things together that are different shapes. So if they're not the same shape, we're going to need an additional convolution that just projects the number of channels to the correct number that we want. So it's going to be nn.conv2d in channels equals in channels. Or so it's just going to go from in channels to out channels. And let's do kernel size equals 1. So kernel size equals 1 is the easy way of just making sure that our image space, right, the height and width of the image will not change. It's just going to take however many channels we have and project it up to the number of channels we want. In this case, we want to go from in channels to out channels. And so we're going to only do this if in channels does not equal to out channels. Else we just want nn.identity, right? So we're just going to use the identity function so nothing happens. And so now what we're going to do is instead of just doing residual connection here, we're going to pass, let's fix that. we're going to pass this residual connection. We can do a quick test here. We can do self.residual connection, and we're going to pass in the residual connection. Or let's call this residual match. Now let's make it a little bit clearer about what's going on. So we're going to pass this residual connection into residual match, grab the shape, and we're going to grab print x.shape, right? And we should see now. She'll give me the error, then update it. But we've seen that we've updated our residual connection, which originally had 32 channels. And because it can't add to something that was projected to 64 channels, the residual connection has now been also projected to 64. So these two things are now the same. And if the same, we can add them together. So this case will only occur when our in channels does not equal to the out channels. So we can now throw a self.residual match around u, and we are good to go. That is our entire residual block. And so we're done there. The other piece we're going to need is an upsampling block. So again, if you remember, in convolutions, if you use a stride of 2, go take a look at my intro to Vision if you don't really understand what convolutions are, or kind of the mechanics of them. But if you use a strided convolution, so a stride of 2, then your image will be half the size when it comes out, right? So if you have a 256 by 256 image and you pass it through a convolution with a stride of 2, then it will output a 128 by 128 image. So you've downsampled by a factor of 2. Now our problem is that, okay, we can go down. What about going back up, right? Because in our decoder, we're going to need to upsample our image back. And so again, this is very similar to your convolutional autoencoder. You can either use interpolation or you can use transpose convolutions. So for the original UNet implementation, they use transpose convolutions, but in modern architecture, specifically for generative models, we end up using upsampling instead because it leads to higher quality images. So we use interpolation instead because it just leads to better images. So we're going to create a class Upsample Block. We'll talk about the checkerboarding artifacting that occurs in generative models when using transpose convolutions, but for today, because we're kind of focusing on image segmentation, we're not really going to care all that much. Do in channels, out channels, and interpolate equals, we'll say false for now, right? By default, we'll set it to false. And so we'll have our super.init, just like that. And what we're going to do is if interpolate, so if we're using the interpolation method, then we're going to do self.upsample is equal to nn.sequential. And in this, we're going to have two things. First, a nn.upsample, and this is brute force upsampling. So it's going to be a scale factor equals 2. We have to pick a mode. We're going to use bilinear. Let's just, you could also use bicubic or nearest. I'm sure different ones have different benefits, so we're just going to leave it like that. And that should be good, right? So that's us doing a upsample factor by a factor of 2 using just an interpolation-based method rather than any kind of learned method. But of course, we want to learn something. So what we do is typically follow this manual upsampling up with a convolution. So now we're going to do a nn.con2d. And this convolution will not change anything except it's going to go from in channels to out channels. Right, so we're going to project our in channels to the out channels with this convolution. And again, we already upsampled by a factor of 2 here. So now that we've upsampled by a factor of 2, we definitely don't want to change anything anymore. So we can just do we can say kernel size is 3 and padding equals same to ensure that the output is the same as the input. The output resolution is the same as the input. Else, right, so if we're not interpolating, then self.upsample will simply be nn.con transpose 2D. So it's a transpose, a learned upsampling using transpose convolutions. Again, it's going to go from in channels to out channels. And we're going to say a kernel size of 2 and stride equals 2. And this will also go ahead and upsample by a factor of 2. You could also do a kernel size of 3, but then you have to use a different stride and you have to also add output padding. And there's a bunch of ways you can get this to upsample by a factor of 2. So you'll kind of have to play with it and see what works. This seems to work fine, so we're going to go with that for now. So we now have our interpolation. We have an upsample method using interpolation or an upsample method using transpose convolutions. And so let's give this a try. Def forward self x, and we're going to return self.upsample x, just like that. So very simple. And so let's give this a try. Let's say our image space was, let's say we had a 64 by 64 image. We want to upsample to a 128 by 128, right? So a factor of 2. So we're going to do in channels is, let's just leave it as 32. Out channels is 32, so we're not going to change the number of channels here. We're just going to upsample by a factor of 2. And what we're going to do is say the interpolate equals, let's do the interpolation method first. So now if we look at this, we're going to see print. Oh, there we go, dot shape. Let's take a look. So when we use our interpolation method, you'll see we're up to 128 by 128. So we took a 64 by 64 image and upsampled to a 128 by 128. So that's our upsampling happening right there. If we don't use interpolation, again, same thing, but this is more of a learned upsampling rather than using a manual upsampling method first and then learning some filters after that. So there you go. These are your kind of two ways of doing it. For the original UNet for segmentation, this is what we use, but this seems to not lead to very good image generations in a lot of applications. At least it's something called the basically this thing called checkerboard artifacting, which we'll look at later when we actually implement diffusion. So in diffusion, in generative problems, we typically use this method instead. It leads to better results. And so we're good to go. We now have our upsample block, and now all we need to do is write our UNet, which is the finicky part. So how we're going to define this UNet is kind of like this. So we're going to do class UNet and then .module definite. And what we're going to provide this is self. In channels is 3, right? So how many input channels do our images have? The ADE20K dataset that we're going to be working with has 150 classes. So there's 150 things that each thing could be, right, in the image segmentation problem. And so we're going to say num classes is equal to 150. I'm going to say that. Then we have our start dim. And so what we're going to do here is we're going to say our convolution. So if we go back to this picture, the first convolution is going to take 3 input channels and output however many start dim channels we say. So the larger that is, the larger that very first projection. Completely up to you. I'm going to just set it to 64. And then what we're going to do is have these things called dim mults. And we're going to set this to, let's say we do 1, 2, 4, 8. So that means the first convolution is after the first projection convolution. It's going to go from 64 to 128. And then we're going to go from 128 channels to 256 channels. And then 256 channels to 512 channels. It's basically the multiplication factor on the original starting dim, right? So there we go. So how many channels do we want in every single block? And this also implies that we have 4 blocks of convolutions happening. So we have this first one, the second one, the third one. And in this case, there's just 3, but it implies how many downsamples you want. So in each of these blocks, we'll be downsampling by a factor of 2. So what that means is that our first convolution will take a, let's say our image was 4 by 3 by 64 by 64. It's going to, the first convolution is going to project this, and let's pick another size. Let's do 256 by 256. So the first convolution is going to take this 4 by 3 by 256 by 256 and project it to 64. And then now we actually start the UNets. So now we have a 4 by 64 by 256 by 256. We're going to have a convolution, which is going to go from 64 to 128 channels, right? So we're going to go from 64 to 120 channels because 64 times 2 is 128. But the images will be downsampled from 256 by 256 to 128 by 128. So every single time we go forward, we increase the number of channels and half the resolution of the image. So pretty standard setup for most of this, neural network sort of stuff. We're also going to provide a residual blocks per group. We're going to set this to 1. So this says that instead of just having 1 block, so this would imply if this is just 1, we'll only have 1 block of convolutions in every single one of these things. So 1 block of convolutions in every single one of these. If we set this to 2, then we would have 2 sets of convolutions in each one of these. And you'll see what that looks like when we implement it. We also have our group norm groups. So this is the group norm num groups. Let's set this to 16, right? This is just what we had from before. Interpolated upsample, we said is false for the standard UNet, so we're just going to leave it as false for now. And then that's it. So that's actually all we need. So we're good to go. All right. So super.init. Now, this is where it gets a little bit finicky. There's actually a lot of ways you can implement this model. I'm going to do it in a way that's more helpful for learning, but probably unnecessary for actually implementing it. But it'll just kind of make clear what's going on. Because the way I like to implement UNet is to make the decoder portion a mirror image of the encoder, right? So we want to make this a mirror image of the encoder, but there is one thing we have to keep in mind. Let's say, as we go down these blocks, let's say this first one has an output of 64 channels by 256 by 256, right? That's the output of this convolution here. And that'll kind of, we store that temporary value so we can concatenate it on later. On this block, we're going to be upsampling to get there, right? Upsampling to get there. So we need to concatenate this and this together, the outputs together. We need to make sure all the shapes match. And actually a better visual for this would be right here. So if we go to UNet for segmentation, I think this will make it a little bit clearer. It's a figure I drew a while back. Here we go. So what you can see here is we have kind of all of these convolutions happening, and we store these temporary outputs as we go. So that means when we start our decoder block, we need to concatenate this thing to this thing, which goes to this convolution, right? So we're concatenating stuff together, which then goes to a convolution. So if you notice, this thing here has 128 channels, and this thing here has 128 channels, which means when concatenating them together, we'll have 256 channels, right? That's how many channels we have. And if we have 256 channels, that means this next convolution needs to accept 256 channels. So that's what makes this a little bit more challenging to implement, because we need to, the input to this decoder is not just the input, it's the input plus, or the concatenation of the input plus the thing we're concatenating onto it. So we just need to track all this stuff, which is why it makes it a little bit easier to pre-compute all this and then set up the convolutions afterwards. So how we're going to do this is we're going to do self.input image channels is equal to in channels, right? So that's how many input channels we have. Self.interpolate is our interpolated upsample, and and actually we don't have anything else. We don't need to store anything else. So that should be good. And so what we're going to do is go ahead and define the UNet right here. So we're going to call this UNet. UNet is UNet, just like that. We're going to leave all the defaults, so that's fine. We can ignore U. And what we want to do first is compute how many channels are there in every single block. So we're going to do channel sizes is going to be equal to start dim times I for I in dim mult. So if we print channel sizes, you will see we get this. So the first block will be 64, the second block will have 128 channels, then 256 channels, and 512 channels. So it just determines how many channels we have at every block, because it's just, this is our multiplier. If I change this multiplier 8 to 16 instead, then we would have 1024 here instead, right? Because it's going to be 64 times 16. If I add more blocks here, right, keep going, then we would have a deeper UNet. We'd have more blocks going on. So there you go. But we're going to leave this as the default, like that. And what we're going to do is set the starting channel size and the ending channel size. We're going to set it to channel sizes 0 and channel sizes -1, right? Because we're going to be starting with 64 and ending with whatever the final one is, right? In this case, 512. So there you go. We're just going to store those. And what we're going to create is the config, the encoder config. And we're going to use this config to build the convolution a little bit later. For now, let's just do self.encoder config, just an empty list. And we're going to do for IDX D, whatever, in enumerate channel sizes. We're going to store first how many residual blocks we want. So in each one of these channel sizes, we're going to have however many residual blocks we want to keep. And so that's going to be, let's do for blank in range residual blocks per group. We're going to have self.encoder config, and I'm just going to store a tuple of information here. The information I care about is what's the input channels and output channels. In our case, each of these residual blocks, we're going to go from whatever the input channel D is to D, so we're not going to change the number of channels. And I'm just going to call this a residual because it's a residual block. So there you go. After that, we will perform a downsample. So we've completed a couple of residual connections. And remember, in every residual connection, we could update the number of channels. We don't here, so that's fine. In this case, we're just going to leave the same number of channels over and over again and leave the image space intact. So we're not going to update the channel dimension. It's going to be the same input channels and output channels. And because we have padding equals same on both of these, we're not going to update the resolution of the image either. So both things are left intact. So the input is the same dimensions as the output. After we've repeated this however many times you want to, we'll then do self.encoder config.append. And now we're going to add in a, so we're going to add a DD again. We're not going to change the number of channels here, but we're going to say this is a downsample block. So this is where we're going to have to add in that downsample convolution. We'll see that later when we implement it. And then lastly, once we're at the end of these channel sizes, right? Once we've kind of looped through all of them, every single time we do it, we need to now update our channels to go from, in this case, if we go back, we need to go from 64 to 128 channels, right? To prepare for the next block. And so now we're going to add in that final residual block, but now we're going to update from D to the whatever the next one is, right? So update the number of channels. So we're going to do if index less than, so we only do this for everything except for the last one, of course, because there's nothing to go to in the last one. So channel sizes -1, so we're going to do it for everything except for the last one. We're going to do self.encoder config.append. And now we're going to go from D to channel sizes IDX +1, so whatever the next number of channels is. And again, this is a residual block, residual. And so if we print out our self.encoder config, it should make it pretty clear of what's going on. List object not callable. Let's see here. Which one did it break on? Dot append. There you go. So our first convolution after we do that initial projection. So we've already taken our 3-channel image and projected it to 64. So don't worry about that. We're starting at a 64-channel image. It's going to go from 64 to 64 as a residual block. And then because we only had one residual block per group, that's it. We only had this one residual, 64, 64, residual block. Then we're going to have a 64 channel to 64 channel downsample. This is going to half the resolution of the image. And then to prepare for the next convolution, the next block, we're going to go from 64 to 128 channels as, again, the residual connection. So that's going to, again, use this residual block, but the in channels is going to be different from the out channels. And now that we're at 128 channels, the next set is going to be the next block. It's 128 to 128. Again, it's a residual block. And then we're going to do 128 to 128, downsample the image again by another factor of 2, and then go from 128 to 256, right? So again, we're going to prepare it with the residual block for the next block, and we just rinse and repeat this over and over again. Now, if I set my residual blocks per group to like 4, right? If we had that many of them, we're just stacking a lot of these. So see, we go 64 to 64, again 64 to 64, again 64 to 64, again 64 to 64. So we just have a bunch of these residual blocks happening over and over again, but once we've repeated them, now we do our downsample to downsample by a factor of 2, and then basically scale the number of channels up to be prepared for the next set of convolutions. And so that's basically it. That is our encoder essentially done. At least the format of it. We still have to define the convolutions, of course. We'll get there in a bit. After that, we need to define the bottlenecks. Self.bottleneck, bottleneck config, empty list, and we're going to do for blank in range residual So the bottleneck is basically however many residual blocks. You can just have one of them. You can obviously make this however you want it to be. I just did it this way. So however many residual blocks per group I said I wanted, that's how many bottleneck layers we'll have. So typically there's just one, so we don't really have to worry about it, but this is fine. So it's self.bottleneck config.append. And we're going to do, remember, we are now at the ending channel. So once we've completed the encoder, we're at the maximum number of channels, in this case 512. So we're at 512. So we can just use this ending channel value here. So it's going to be from ending channel to ending channel, because we don't want to change, let's put another tuple, ending channel to ending channel, because we don't want to change the channel dimension here. We don't want to change anything really. We want to keep the resolution intact. It's just our bottleneck layer, so residual connection. So there we go. We're just going to repeat that as many times as we want. And that is basically what we have for the encoder and the bottleneck. And this is the easy part. Now for the decoder, this is where it gets a little bit challenging. Because again, remember, we need to make sure that we've done this. We've started from a 128 by 128 with 3 channels, and I said we kind of has initial convolution that projects it, and we just repeat these convolutions over and over again, and we get this. But now, as we upsample our image, kind of one block at a time, we need to make sure that our convolution accepts the dimension of the input concatenated with the thing we're grabbing from the encoder, right? So these two things have to match up. And so we just need to ensure that everything lines up. The easiest way to do this is just we're going to set outdim. Let's just set this to ending channel size. And what we're going to do is create something called the reversed encoder config. It's just going to be the self.encoder config flipped around. Because I said that I want to make my decoder a mirror image of the encoder. So let's just backtrack through exactly what we built here and just see what we can make. So we can now do self.decoder config, it's an empty list. And we're going to do for index, and we're going to store here. Remember, each of these things in this, in each of these tuples, we have a tuple and a name. So let's just call this like metadata and call this the type. So we're going to do metadata type enumerate our it's now going to be the reversed encoder config. And let's just go ahead and print out the metadata and type just so it's clear. It should look exactly like what we had made earlier, just in reverse order. So it's a 512 by 512 downsample, 512 by 512 residual, 256 by 512 residual, ... So this is exactly what we had before, just going in the reverse order, right? So we started from here and went up in the encoder. Now our decoder is going to look exactly like this, but it's going to go the opposite direction. And that's the key idea. So what we're going to do is create, this metadata is 2 things. So it's going to be enc in channels and enc out channels equals metadata, right? There's 2 numbers in there. In this case, they're all the same, 512, 512, but sometimes it'll be different, right? 256 to 512 in this case. And now that we have that, we need to create our number of channels after we concatenate. Like how many channels would we have if we concatenated? And so right now, our data is in this output dimension. So whatever our final channel was, in this case 512, our bottleneck was going to output something at the ending channel size, which is 512 in our case. So the bottleneck will output something in 512, and the encoder also had, so before the bottleneck, the encoder also ended with something with channel size of 512. And we can see that right here, right? The final, so this is the last thing in the encoder, outputted something of the dimension or of the number of channels of 512, right? So there we go. It's a 512. And so what we need to do is take this 512 channels here and take the 512 channels from the bottleneck and concatenate them together, giving us effectively 1024 channels, right? So it's going to be 1024 channels. So what we're going to do is say the concat num channels is going to be equal to the outdim plus the enc out channels, right? That's going to be our 512 right there. How many channels did we get from the final block of our encoder? and how many channels do we have from the final output of the bottleneck. And those two things concatenate together. And that's basically this, right? So we have one convolution here in the bottleneck. It's going to output some number of channels, and we're going to concatenate this number of channels to our encoder number of channels, right? That's going to concatenate together. So now that we have that, we've concatenated them together, we can now do self.decoder config. And we can do our, here we go, we're going to do concat num channels, that's the input, and we're going to output the enc in channels, because we're reversing, right? We're going the other way. So if this thing was started from 512 and went to 512, that was that convolution. Now we're going to take the 1024 in this case, with the concatenation, and project back to 512 here. So we're going to kind of just go in the reverse order. In the next one, again, in 512, 512 would be the same thing, ... We're going to repeat this over and over again. And so that's going to go ahead and just kind of go the other way, just reversing, making it a mirror image essentially. And again, this is a residual connection, residual, just like that. So we have our decoder config. Now there's one other thing to keep in mind. Remember, the bottleneck here did not change the height and width resolution of the image, right? That never changed. And so the height and width of the output of the encoder is the same as the height and width as the output of the bottleneck, which is why this concatenation will be valid. But notice here that this was a downsample operation in the encoder, which means the original output, right, basically what came out of the previous thing, was twice the size. So for us to be able to concatenate this stuff onto the decoder again, we need to go ahead and upsample. So anytime we did a downsample here, for us to concatenate the thing that this thing downsampled, we need to upsample that to match the image space. So this is basically the other sanity check. If type equals downsample, so if we had done a downsample, then it's time to do a upsample. We're going to do self.decoder config .append, and we're going to store in here a there we go. And we're going to not change the number of channels. So it's going to be enc in channels to enc in channels. And this is going to be a upsample. So this should be a upsample, just like that. So if we had done a downsample, we want to do a mirror image. So we want to add an extra upsample block to get it to match. And so now we are good to go, right? So this is what we have. And we added in this extra upsample. And we should have everything we need. The last step is we need to create our outdim is now equal to the enc in channels, right? Which makes sense. Our encoder input channels is what this thing outputted, the final thing of our decoder. And if there's a downsample, then that's what it would have outputted, which means the output dim at the current stage, right? Whatever block we're on currently will be this, right? That's what we have. And so we've just updated our outdim to become the new number of channels for the current tensor. And we just rinse and repeat this over and over again. And you'll see that if we print self.decoder config, looks like I forgot that again. Sorry. There we go. Decoder config. It's going to go from 1024 because we concatenated something on down to 512. And then we're going to have a 512 by 512 with an upsample block because we had done a downsample here. So it needs to match. And then we end up with a 512 by basically a image. This will output a image size that's twice as big with channel of 512. And that's great because this thing was twice as big, right? This is the output of this convolution is what was downsampled here. So now we can go ahead and concatenate this on. Again, it's 512 channels here. So we're going to concatenate to this 512 here, this 512 here, again, giving us 1024. And we just want to work backwards. So this was 512, so we're going to output to 512 again. And then again, 1024. We have 512 things here, the output. And we had 512 things here from this output, the output of this convolution. And so then we're going to take this 512, this 512, this 512 here, and this 512 here, concatenate them together, giving us 1024, but we want to work backwards. So this thing had 256 channel input. So we're going to output 256 here. And just rinse and repeat this down the entire model until we're back to where we started. And so that's basically it. That's the main idea. And so now that we have that, we can just go ahead and set up our actual convolutions, which is exciting. There is one convolution that we are missing, one thing here, but we can add that in a little bit later. So we'll come back to that. We're going to add one more thing to the, actually, yeah, let's just go ahead and add it. So remember, this stuff is already starting from that initial convolution. So we start with 3 channels and we project to 64 channels. And then after that, all of this stuff began. So that's when all of this is going to happen. But we still have that first convolution that went from 3 channels to 64. We want to concatenate the information from that first convolution on as well. So we're just going to add that in manually. Self.decoder config, or let's do it as concat num channels is equal to starting channel channel size. It's whatever. We had 3 channels in this case, so we're going to have 2 of them concatenated together, so it's going to be times 2. And we're going to do self.decoder config.append. And again, it's going to be just like before, concat num channels to starting channel size. And this is going to be a residual block. So this will just handle that special case for that first convolution, which isn't really in here yet. And we're going to start defining it. So this will now start to actually come together because we're going to implement this model, right? So we're going to do self. So this is our actual model. So everything else has just been the setup for what we're trying to do. So we're going to do self.conv in proj, right? It's going to be nn.conv2d. And it's going to be self.input image channels, whatever it was. That's the input. And then there's going to be the starting channel size. So we projected 64, and we're going to do kernel size of 3, and padding equals same to ensure that we don't change any of the image space, right? We want to keep the image space size, the resolution the same, but update the number of channels to be whatever the starting size we want, starting number of channels. And so then we'll have our self.encoder is nn.module list. And the cool part is we already did all the work, right? We defined the encoder config here, so we just need to loop through the encoder config and just actually create those convolutions. So we can do for metadata type in self.encoder config. Right, we're going to loop through, and we're going to do if type is residual. So if it's a residual block, because remember, our encoder has only 2 types. We have residual blocks and downsamples, right? So if it's a residual block, then we can go ahead and do in channels, out channels equals our metadata. That's what's stored inside that thing. And that's basically what we have. And so we can do self.encoder.append our residual block, right? The residual block that we created earlier with in channels and then out channels and then group norm num groups. So that's our full setup. Group norm num groups. There we go. Right, so that's us adding that residual block in for this specific, if it's a residual block. Otherwise, if it's not a residual block, it's a downsample block. So if type is a downsample, which is the only other thing it could be, we're again going to do in channels, out channels is equal to metadata, because that's what's stored. And we're going to do self.encoder.append a downsample convolution, so nn.conv2d. And it's going to have in channels, it'll have out channels, it'll have a kernel size of 3, stride equals 2, padding equals 1, which is a standard formula, this 3, 2, 1, essentially on like even numbered resolutions. 3, 2, 1 always downsamples by a factor of 2. So we'll do kernel size 3, stride 2, padding 1, and this will downsample because we have a stride of 2 by a factor of 2. And so we are now good to go. So that is our encoder. So print self.encoder, and you'll see that we have all of these convolutions. We have a residual block. So we have a residual block. Then we have a downsample block. Then we have another residual block. And then let's see here. Which one am I missing? Oh, right. So we have the initial residual block. Am I missing one? Self.conv in proj is not defined here. Only the module list is shown. Oh, because I only print self.encoder. That's my bad. Okay, yeah, no. let's maybe print out UNet instead. Print UNet. There we go. So we have our convinge proj that's going to take 3 channels, project to 64, and that's basically it. And then we have our encoder, which is basically a residual, then a convolution, then more residual blocks, and another convolution downsample, and then more residual blocks, and another convolution downsample, so on and so forth. Just repeat it over and over again, right? They're just stacked on top of each other. So that's our encoder. Now we similarly have our bottleneck. Bottleneck's easy, so self.bottleneck, and then again, module list, and we're going to do for, in this case again, in channels, out channels, and we'll have a type, but we don't really care what it is here because it's only residual blocks. Just how many do you want? In self.bottleneck config, right? So how many do we want? In this case, we have our bottleneck, which we defined right here, right? It's just a stack of the same residual block over and over again, and they're residual blocks, so we don't really, that's the only thing it could be, so we don't really care what it is. And we're going to just do self.bottleneck.append, and we're going to do a residual block once again, and it's going to be in channels to out channels, and then group norm num groups, just like that. So we are good to go. That's the bottleneck. And then lastly, we have our decoder. So self.decoder. Again, as you can see, it's basically the same thing over and over again because we've done all the hard work earlier. For again, this is going to look a lot like this, so we can go ahead and copy it in. For metadata type, this is now going to be the decoder config instead. Again, if it's a residual block, exactly the same. Grab the input-output channel, append on a residual block. That's what we have here. Otherwise, right? Otherwise, if it's a upsample, because remember, our decoder blocks is either a residual or it's a upsample. Those are my 2 types. So if it's an upsample, then go ahead and just do that. So we have our upsample, and we just need to add in our upsample block here, which we also defined, right? That's going to be our upsample block. And this is going to be in channels, out channels, and interpolate is equal to self.interpolate, right? Whatever, if we want to use the interpolation mode, or if we want to just use transpose convolutions, it's up to you. And so now we should have our full model ready to go. Almost. We actually have one more step to go, but it's an empty module list. Let's see. Whoops. These should be all appending to the decoder. There we go. So we now have our decoders as well. Everything is here. So we have all of our decoder layers. Good. And the final thing is we need to actually predict how many, for every class. We need to predict this is image segmentation. So we need to predict for every single pixel, what class is it? And so that's going to be self.con out proj. And actually now is probably a good time to mention this. Image segmentation. If you've never seen, hopefully you already know what image segmentation is or have seen pictures before, but this is what image segmentation basically always looks like. You have a picture, and for every pixel you want to classify what class is it? Like, is it a car or a train or road or person, right? That's standard image segmentation. So that's exactly what we're doing. We need for every pixel, what can it be? And so what can it be is just dependent on we can just make it the number of channels. So we're going to do equals nn.con2d. We won't need this when we do the diffusion later. So this is fine, but for now we're going to do it because we're doing segmentation. In channels is going to be the starting channel size because that's all of this has now ended up with a final 64 channels, right? That's where we're at. And so now we're going to go from that 64 channels to the number of output classes that we have. So our output's going to be out channels is going to be num classes. In our case, it's 150. Oop. Deleted something. There we go. Out channels is equal to the num classes. And again, kernel size is, let's just say 3. Or you can do kernel size is 1, right? Just keep it simple. So it's just output the number, just projected to the number of classes that we have. And so now that we have that, we are good to go. That's everything we need. And so let's write our forward function. And so what we're going to do is create a list here called residuals. And we're going to store our residuals. So again, if we go back to our figure, every convolution, we want to just store these intermediate outputs so we can concatenate them in the future, right? As we go through our decoder block. So we're just going to create a list here, an empty list, and just kind of store them there. So we're going to do x is equal to self.conv in project x. And let's follow the, well, I guess we could follow the shapes, but it won't really, there's a lot of convolution, so it might be less helpful to print everything out. But we take our data, which is in this shape, and it goes to that very first convolution. And what we're going to do is store in our residuals here, dot append x. We're going to go ahead and store that x in here. And so we're good to go. And now we're going to just loop through every single layer of the encoder and store our value. So we're going to do for module and self.encoder x module x. We're going to pass it through, and we're going to do residuals dot append x. We're going to go ahead and store them. And let's go ahead and print out x.shape here after we kind of perform all these convolutions. So we're going to print UNet. We're going to pass in rand. And let's go ahead and see what that looks like after we pass all that in. And so we're down to a 4 by 512 by 16 by 16, which makes sense. We started with a 256 by 256, and we did 4 sets of downsamples. So we go from 256 down to 128, down to 64, down to 32, down, right? So we're repeating our stack over and over again. And so now that we've gone ahead and done all of these downsamples, and we have everything we need, we can go ahead and we have 512 channels right here, 512 channels. And so now that we have that, we're going to pass it through a bottleneck. So very simply, for a module in self.bottleneck, we're going to do x module x. We don't need to store these. We only store the residuals from our encoder and that initial convolution. Good. So now that we have that, we need to do our decoder. But the decoder is the tougher part because we need to concatenate stuff as we're going along. So we're going to do for module in self.decoder. Right? We're going to do, first of all, if it is a residual block. So if is instance, because remember, these can either be two things. It's either a residual block or it's an upsample block, right? So if it's a residual block, so if the module is a residual block, then we need to do that concatenation that we talked about. So we're going to do residual tensor. Residual tensor is going to be our residuals dot pop. And dot pop is just going to automatically grab and remove the last thing from this list and just store it in here. So there we go. And we're going to do x is equal to torch.cat. We're going to concatenate on x, right? So to the original x, so to this x, we're going to concatenate on whatever was stored inside this residual, right? The last thing that was in that residual. And so we're going to store on our residual tensor. We're going to go ahead and do that. And we're going to do it along dim equals 1, along the channel dimension. So it goes batch is dim 0, channel is dim 1, then height and width are dim 2 and 3. So we're going to do along the channel dimension. And so that goes ahead and concatenates. So this is that concatenation operation that we've been talking about. And then we can do x equals module x. Go ahead and take the data and actually pass it through that module of the decoder. Now we only do this for the residual block because we have paired every single residual block from the decoder to the ones in the encoder. So we're good to go. Now the other blocks we have are the upsamples, so else x equals module x. So the only other blocks we have are upsample blocks in the decoder. And those are just to ensure that the height and width dimensions match for the next residual block. Because again, these were all downsampled as we were going. We need to upsample as we go here as well to make those concatenations valid. And so now let's see if this worked out. Print x.shape. All right, there we go. That worked. So we are now back to 4 by 64 by 256 by 256, right? That's what we have. And this will, with all of these concatenations, basically working out. So we can actually print them here. We can do print x.shape, residual tensor.shape. Let's just look at all of them as they go, and it will hopefully clarify everything. So there we go. The first one, right? The output of the bottleneck was 4 by 512 by 16 by 16. And our last output of the encoder was also 4 by 512 by 16 by 16. So when we concatenated them together, we will get basically a 512 and 512 concatenated together to give us 1024. And then again, that 1024 was passed to a convolution that took 1024, projected to 512, and we get this new 512, which was then concatenated to the next thing. And we should repeat this over and over again for everything that we have. Good. So now that we have completed our entire process here, we just need to do the final convolution. X is equal to self.con outproj x. And we can print out finally x.shape just as our last verification. Oh. There we go. We have 4 images, batch size of 4, 150 possible classes that each image could be, and then 256 by 256. So that's what we have. And we are basically done, right? That's everything we had. And we can return x. And that's the implementation of the UNet. And this is about 90% of what we will need for the diffusion implementation in the future. But again, for today, we're going to need to do image segmentation. So for segmentation, we need to go ahead and write the data loader. Data loader is pretty straightforward, but there's a couple of little details that we're going to add in. So we're going to do class. Actually, let's do import OS. We're going to need import numpy as np. From pill, import image, import random, import torch. From torch.utils.data, import dataset. We need from torch vision we need the transforms, import transforms. And we're going to need import torch vision transforms.functional as I'm going to call it TF. So what we're going to do is create our class ADE20K dataset. So standard dataset setup. So we have an init. And in this init, we're going to have self, the path to data. We're going to have the image size. So I'll show you what the data looks like in just a bit, but you can download it from just look up ADE20K dataset and it'll show up and you can just download it. We're going to have a random crop ratio. I'm going to set this to 0.2 to 1. We'll talk about what that is in a bit. And inference mode equals false for now. So you'll see why we have those in just a second. And so what we're going to do is self.path2data is the path to data. Self.inference mode is our inference mode. Self.train is train. All right, so we also need to throw here path to data. We also need a train equals true, right? So are we on the training split or are we on the validation split? So we'll see that in a bit. So self.train is train. Then we'll have self.image size is our image size. And then finally self.min ratio and self.max ratio is equal to random crop ratio. We're going to go ahead and split that tuple up and we are good to go. And so we're going to first do if train. So for the training split, then our split is equal to training, else split is equal to validation. So the ADE20K dataset has already been split into training and validation sets. And so the folder for training is called training and the folder for validation is called validation. So we can do self.path to images is equal to os.path.join. And it's going to be self.path to data. There's going to be a folder called images. And then inside that, there's going to be the train and val splits. So it's going to be just like that. So it's the path to wherever the data is, our images, the images folder, and the split. And then similarly, self.path to annotations, which is basically exactly the same resolution as our images. It's just for every single pixel, it identifies what class label is it. Like, is it a dog? Is it a car? Is it a road? Whatever the class labels are. So path to annotations is os.path.join, self.path to data. Annotations is that folder. And then again, whatever split we're currently looking at. And so there we go. So we're going to go ahead and get all of the unique file roots because they use the exact same naming strategy. So we can go ahead and actually look at ADE20K. We can see the images folder, and inside images, you see there's training and validation. Let's look at validation. And you can see there's all these pictures, right? Here is a example picture from this data set, right? So make it bigger, right? So here's an example picture from that data set. And for each of these pictures, we have a corresponding segmentation mask, right? That identifies what each of those labels are, right? So you can see these are like windows and whatever. So what each of those labels are. So you have these segmentation masks. And so what we need to do is just set it up. So you can see the naming scheme and everything is identical. So we're just gonna get the file roots, and then it's just a matter of, so in this case, like this is called ADE val 0000 whatever 3. And then in images, if we go to validation, it's exactly the same name. It's just these are JPEGs and the other ones are PNGs. So that's the only difference. So we're gonna grab the file roots, basically the name, and then we can individually access them as necessary. So we're gonna grab file roots. It's gonna be self.file roots. It's going to be just path, and we're just gonna do dot split. We'll split it on the period and grab the first thing for path in os.listdir self.path to images. We could have also done annotations, it doesn't matter. So let's go ahead and kind of give this a quick test here real quick. So we're going to do if name equals main. We're going to do path is equal to, I think that's correct. Let's give that a try. So we're going to do ADE20K dataset path. So that's our dataset. Let's give this a try. Python os.path.join. There we go. No such file. Did I go 1 too deep? Okay, yeah, that worked. Okay, good. So if we print out self.file roots, you'll basically see a list of all of the files, right? So these are all of the images in the training split, for example. So that's our list, and then we can just grab, you know, if it's the annotation you want, that's a PNG in the annotation folder. If it's the image you want, that's a JPEG in the image folder. So there we go. And so all we need to do now is, I believe we have everything we need. Good. So we're just going to go ahead and just define some other stuff, our typical transformations that we want. So we're going to do self.resize. Resize is equal to transforms.resize, and we're going to go from self.imagesize to self.imagesize. So that's our resize operation. We'll have a self.normalize, right? We typically want to normalize our images. Transforms.normalize, and we're going to use ImageNet normalization, so I don't want to copy all of these constants in, but it's just standard mean for the RGB channel and standard deviations for the RGB channels. So there you go. We'll also have our random resizing. So this is something new. You may not have seen it before, but a typical strategy used in segmentation is, instead of just trying to train the segmentation on the entire image every single time, take random crops of the image, right? That's the main idea. So let's go ahead and use a technique called random resize crop. Self.random resize can be transforms.random resize crop. And in the random resize crop, there's basically a couple things we need to provide. First of all, size. So we may go and grab a random crop of our image, but we want to interpolate that back to the actual 128 by 128 size that we want in the end, right? So whatever it is. So we just need to make sure we set it to that. So we're going to set size is equal to self.imagesize to self.imagesize. But another question is, when we take random crops, what range do you want it to be? So if you can see here a scale of 1 will just take the whole image. So it'll crop a random portion of the image and resize it to a given size. That's the main idea. But when it takes a random crop, it's like, well, what range do you want to take? And so we can change the scale. By default, the scale is 0.08 to 1. That'll work probably fine. I set it, so let's just set this to the default. 0.08 to 1, whatever. And so all we need to do is set the size is equal to, or not size, sorry. The scale is equal to just our self.min ratio to self.max ratio. This should be ratio. Right, so that's it. So we're going to grab, this transform will automatically grab random crops of the image and then resize them to the size that we want. We'll also throw in a self.horizontal flipping, right? That's pretty important. We're going to do transforms.random horizontal flip, but we're going to set the probability of this to 1. You'll see why we do this later. Typically it's 50-50, right? Like half the times you flip, half the time you don't flip. I am just creating this here, so we'll always flip, and I'll do the random part myself, and you'll see why we do that. And then self.toTensor, of course. It's going to be transforms.toTensor. And so these are all of the transformations that we're going to need. And so let's go ahead and actually build the data set. So def len. Len is easy. We just return len of our self.random, or not random, file roots, right? So however many file roots we have is how many samples we have in our data set. So there you go. And then def get item. So self index. And so what we need to do is first load the file root, right? So this index is going to go through all the file roots. We're going to do our file root is going to be self.fileroots index. So grab whichever file root it is. And then we need the path to the image and the annotation. So our image is equal to os.path.join. And it's going to be self.path to images. And the name of the file was the file root dot JPEG, right? They were JPEG files. And similarly, the annotation was os.path.join. It was self.path to images. And it's going to be our, or sorry, not path to images. Now it's going to be path to annotation. And it's going to be, again, f string. It's going to be, again, the file root, but it's going to be .png because our annotations were PNG files. The images were JPEG files. And let's go ahead and load both of these. So we can do image is equal to image.open image. And we're just going to make sure, for some reason, if it's not, these are all RGB images, so convert it to that. And our annotation is, again, image.open n. So now that we have that, let's just take a look what this looks like. So print image, print init. So we're going to do data set. Let's just do data set 0. That should work. So print out 2 pill images, right? We can see there's 2 pill images. And so that's it. And we can convert these to dot array, maybe? Is that what it was? Okay, it's not array. That's okay. We can import, already imported numpy above. Okay, we're good. So we can do np.array. Convert it to a numpy array. And you can see at every single pixel, we have what is the class label. Like, what is it? Is it 0, 6, whatever? So whatever it is what it is. So that's our, that is our image and its corresponding annotation. For every pixel, what is it? And so now that we have that, let's go ahead and just set up our image transformations. And this is what makes it a little bit challenging, because if we do random cropping on our image, like the original image, we need to make sure we grab the same random crop in the annotation, right? They have to match because we have to grab the correct one. And if we do a random flip on the image, we have to make sure we randomly flip the annotation as well, because they're pictures and they go together, right? At the pixel level, they go together. So any operation, any kind of transformation, any shifting, any rotation, anything I do to my original image has to be done to the annotation identically. So that's why it's just a little bit more complicated, but we'll get through it just fine. So we're gonna do if self.train. So if we're in training mode and not self.inference mode. So if we're not if we're not inferencing or anything, then what we're gonna do is half the time we're going to use the entire image, and half the time we're going to do a random crop, right? That's kind of the name of the game here. So we're gonna do if random.random, which is samples a random number between 0 and 1. If it's less than 0.5, so there you go, half the time, so it's uniform random. Then we're just going to do simple image is equal to self.resize image, and our annotation is equal to self.resize annotation. And that's it. It's just going to go ahead and resize our image and its corresponding annotation down to the image size we want, and we're done. It's as simple as that. Otherwise, we have to do a random crop. So what we're going to do is we can do it actually like this. We don't really care. Actually, to be fair, we didn't need to use this here. We didn't actually need that. So, okay, that's fine. We just have it. We need to, let's just do this. So we're going to do min side is equal to min image dot size. So what we're going to do is find what is the smallest size of the image. There's some height and width. What is the small? Is it taller than wider, or is it wider than taller, right? So what is the min size? So whichever dimension is smaller. And then we're going to do a random ratio is going to be random dot uniform, and we're going to randomly pick some number between self dot min ratio and self dot max ratio. It's just like that. So some number between, in our case, 0.08 and 1. So yeah, we're going to pick some random number in between the two. And now that we have this random ratio done, what we're going to do is our crop size, right? Our crop size is going to be the min size times the random ratio. So this is ensuring by the largest size that we will have will be no larger, right? So the crop size, the largest the crop size can be no larger than the smallest dimension. And this just makes it easier to crop. So we're never like, you're not cropping more than there is image. So we're good to go. So now that we've computed our crop size, we can go ahead and get the parameters of that crop. So what that means is we can do I, J, height, width. So ij is the center and the height and width is the height and width of the crop. It's going to be transforms dot transforms dot random crop dot get params. So this is a function or method built right in. And we're going to say for this specific image, I want an output size, a final output size of crop size by crop size. So this is going to go ahead and take a random crop of my image, right? Based on this crop size. So I've told my random crop that I want you to take a random crop of this size from my image space. And so we're good to go. And so now what we need to do is actually do that random crop. So we're going to do image is equal to tf.crop, and this is the functional form of image transforms. We want a random crop image with I, J, H, W, which is basically our center and then the height and the width of that crop. And then similarly, our init is going to be tf.crop, and we're going to, again, crop our annotation in the exact same way, because anything we do to our image, we also have to do to our annotation. So now we have grabbed corresponding random crops of the image and the annotation. But now that we've taken the random crop, we need to actually resize it back to the actual size we want. So we want our images to be 128 by 128, so we can use interpolation. So this is basically what I've done here, is basically what this method would have done. It's just this method would have done it to only one thing, and we need to apply the exact same set of random cropping, to image and annotation. So we just split it up and just did it manually ourselves. But of course, they're identical. And so now that we have that, we can do image is equal to self.resize image, and then our init is equal to self.resize init. Right, so we're going to go ahead and resize these crops to the actual image size we want by using some interpolation method. Also, so this is so again, if we sample a number less than 0.5, use the full image. Otherwise, do a random crop and then resize to the image space we want. Also, if random.random less than 0.5, so if it's less than 0.5, we're going to do image equals self.horizontal flip image, and our init is equal to self.horizontal flip init. So this is why we set init, or the horizontal flip probability, to just 1, because I want to make sure that every time I say do a horizontal flip, it does a horizontal flip with 100% probability, because I've done the random sampling here, because I need to apply that same transformation to both of these. So we're good to go. Now, if we are not, so if we're in validation mode or if we're inferencing, so else, right? So if we are not training essentially, or if we're on the validation set, then we're going to do image is equal to self.resize image, and our init is equal to self.resize Enit. So when we're just inferencing our model, we want to inference on the full image. We don't want to do all this random cropping stuff, right? To get a good evaluation of how the model's doing. So we just go ahead and resize it, and we are done. Lastly, we need to, so these are still images, right? They're pill images. So we just did all this stuff. We need to convert it to a tensor and normalize it. So we're going to do image is equal to self dot to tensor image, right? Convert it to a tensor. And our init is going to be self, or it's going to be, so all we need to do here is just torch.tensor. So because this is a array of integers. Remember, this operation here will scale everything between 0 and 1. We want to leave these numbers alone. We just want them as integers. So we're going to convert to an np.array, init, and we're going to set the d type to torch.long because that's what labels need to be in when we do cross entropy loss in the future. So there we go. We have our annotation. We basically took our annotation, which is a pill image, convert it to array, convert it to a tensor with long d type. So integers, basically integer type. One other thing, and this is another important part to keep in mind, our images. So here's actually a quick snippets from the scene parse. So this is basically the scene parsing data set that we're working on, right? So you can also find information about it here. In this, you can find all the class labels. So you can see the class label 1 is wall, 2 is building, 3 is sky, 4 is floor, ... right? So these are all the different class labels that this thing can be, or what these images can be. Notice that it starts at 1 and goes to 150, right? It goes from 1 to 150. So this is fine, except our data, right, or the typical way we work with it is we start from class 0 and go to 149. So it's like off by 1, right? We want to start at 0 and go to 149. There's also another class. If you remember from our thing before, there's actually zeros in here. You can see there's zeros here. So why are there zeros when 0 is not even one of the class labels? Notice there's no 0 in here. And that's because 0 is like background/other. Like it's a class label that doesn't really exist. So these are unlabeled pixels is basically the way you can think about it. So what we need to do is, first of all, our actual labels that go from 1 to 150, we need to make them go from 0 to 149, right? Because that's what our cross entropy loss will expect. So what we're going to do, init is equal to init minus 1. So this is going to take our init, which goes from 1 to 150, and it's going to now go from 0 to 149. But our init also had that background label 0 in it. So our 0 now has become a minus 1. We're going to indicate to cross entropy loss later to ignore that. So we're going to ignore that label altogether. So we're good to go. Or we could do init, where init equals minus 1 is equal to negative 100. So this would set all those background pixels to negative 100, which cross entropy loss by default will already ignore. So we wouldn't even have to worry about it, but that's fine. We're going to leave it like this. Also, we need to normalize. So our image is equal to self.normalize our image. Gone ahead and do that and return our image and the init, and we are done with our data loader, or data set in this case. So let's do this. For sample in dataset, print sample 0 and print sample 1 and break. Right, so we're going to go ahead and take a look at what this looks like. Hopefully this works. Looks like we have a bug invalid combination, IJHW. Let's see here. torch.randint. Oh yes, this has to be an integer, right? Otherwise this won't work. So let's convert this. It's just the wrong type. Okay, good. So we have our image pixels, and we have for every single pixel its label of what is it, right? So we are now good to go. So we can see 5s here, right? Let's go back to our thing here. So the 5 in our thing is after we subtracted 1, so it's really 6. And so 6 is ceiling, which kind of makes sense. It's at the top of the picture, so ceiling is kind of obvious. So looks like it's more or less working. We have our everything we need, and we can also double check the shape of it, right? Dot shape, and they should be the correct shape. They should be 128 by 128 images. As you can see, it's a 128 by 128 image, and this is just a 128 by 128 set of labels. And so we have our data loader completed. Nice. All we need to do now is train the model, which is always the least interesting part of our implementation, but let's go ahead and do it. I'm going to go ahead and just copy all of this stuff in, everything we're going to need import-wise to train. And we're going to do from Dataloader, import the ADE20K dataset that we wrote, and from model, we're going to import the UNet model that we just wrote. So those are all the things we're going to need. And then, of course, our path to data was the data ADE20K dataset. So there we go. That is our setup. Let's go ahead and write the training script. Def train. And our training is going to need a couple things. So first of all, batch size. Let's say we want 64 samples in a batch. Our gradient accumulation steps. Let's just do, I don't know, we can just do 1. It doesn't really matter. We're going to have a learning rate. Let's set it to 0.001. We'll have num epochs. Let's say 100. Train for 100 epochs on this data set. Image size is 256, right? So that's the image size we're working with. And then we have our experiment. Do I even care about logging? Not really. I'm not going to care about logging here. You can look at my code and see if you want to look like, if you want to also, whatever, I'll add it. Experiment name is, let's just call it UNet train, whatever. All right, we'll just throw it in there. It's fine. Try to keep it clear. So that means we need to add another folder in here called workdir, where we'll store all of our weights and checkpoints and that sort of stuff. All right. So we need our accelerator equals accelerator, and we'll just do our gradient accumulation steps is equal to the gradient accumulation steps. Oh, accumulation steps. Good. So that's our regular accelerator for distributed training. And now we're going to, if you don't know what accelerator is or what Hugging Face accelerator is, I have a whole video on it. It makes distributed training very, very simple. So just go ahead and take a look at it there. But we'll just keep going. Path to experiment is going to be os.path.join. We're going to look in our working directory and then the experiment name. And so we're going to do if not os.path.exists. So if the path to experiment doesn't exist, we're going to do os.make directory path to experiment. There we go. So just go ahead and create that working directory folder to store checkpoints in. So now that we have that, what we need to do is load our data set. So what we need is our micro batch size. So remember, our batch size, we said I want 64, but let's say I had gradient accumulation steps of 2. That means I want to do a batch size of 64, but in 2 steps. So each step would have 32 samples in it. So we're going to do a micro batch size would be just our batch size divided by the gradient accumulation steps. So there we go. And so our train data is going to be the ADE20K dataset. It's going to be the path to data that we indicated above. This is going to be the training split, and then image size is equal to image size. And then similarly, our test data is equal to the ADE20K dataset, path to data, train equals false in this case, and then our image size equals image size, just like that. And then our data loaders will be the train loader is going to be the data loader, train data, batch size is equal to the micro batch size. We'll make sure we shuffle, right? We want to randomly shuffle our data. And we can say num workers is like 8, whatever. And then our test loader is going to be data loader, test data, batch size is equal to micro batch size. Oh, there shouldn't be a equal there. When we're evaluating, we don't really care about shuffling, so we can say shuffle equals false, and num workers equals, again, let's just do 8. All right, good. So we have everything we need. It looks like there might be a small issue here. What's going on? Did I miss a parenthesis somewhere? Let's comment you out real quick. Everything looks fine. Okay, I guess we'll, oh, right here. There we go. All right. So that is all of our data loaders. we also have our loss function, right? So our loss function is going to be nn.cross entropy loss. And we want to make sure ignore index is -1, right? So any label that's -1, it's just background unlabeled stuff. We don't need to compute loss for it. Now, I'm using cross entropy loss here. There are all sorts of loss functions for segmentations. There's like the dice loss, and there's all sorts of loss functions you can use for better segmentation. Cross entropy loss is kind of the most simple one, so that's what we're going with, just to keep it simple for today. Because again, our main goal is to get to diffusion. This is just kind of a nice to know on the way there. So model is equal to UNet. And we're going to say in channels is 3. Num classes was 150. The start dim was 64. Dim mult, I set it to 1, 2, 4, 8. We can leave it like that. And we are good to go. That is our model. Similarly, we have our optimizer. Optimizer is going to be optim.atom.w model.parameters. And learning rate is equal to LR is our learning rate, just like that. And so now that we have everything, let's go ahead and just prepare everything. So this is how Accelerator converts things to distributed training. We'll have our model, our optimizer, our train data, or I called it train loader, test loader is equal to accelerator.prepare. And it's going to be model, optimizer, train loader, test loader, right? So we're going to go ahead and do that. This is just standard Hugging Face accelerate stuff. So again, take a look at that video if you've never seen this before. And we're just going to quickly just write a very simple training loop here. So we're going to do for epoch in range 1 to num epochs plus 1, whatever. And this way we can just print out accelerator.print training epoch. We're going to do from epoch out of num epoch, right? So just print out whatever we're at. And we have a little bit of logging stuff going on here, so nothing too crazy. Train loss, test loss is going to be 2 empty lists. And we'll have our train act, test act is 2 empty lists. Now, accuracy is not a good measure for segmentation. You're better off using something called intersection over union. Again, those are easy things that you can add in. Torch metrics already computes these things for you. Hugging Face evaluate also has mean IOU built right into it. So you can just go ahead and use those methods and add them in if you want. But for now, we're going to keep it simple. We're going to do accumulated loss is 0. We're going to just create some places to store some stuff. Accumulated accuracy equals 0. This is in case we're doing actual grain accumulation, then this would matter. And then our progress bar is going to be a TQDM, right? On range, len, train loader. And remember, the train loader is based on the mini batch size, right? So whatever micro batch size that we picked. In case we actually have a micro batch size that's different from the batch size. So if, for example, if the batch size we want is 64, but the micro batch size is 32 because we wanted 2 steps, that means the train loader and the test loader are twice as long as they should be, right? They're because we have twice as many smaller batches in it. So we just need to make sure we, when we do our progress bar, it shouldn't be the len of the train loader, but the effective length that we want in the end. So it's going to be len train loader divided by gradient accumulation steps, right? That'll go ahead and just get it all correct. And disable is equal to not accelerator.main is main process. So we only want this to happen. Again, remember, everything's happening on 2 GPUs. So accelerator.print and accelerator.isMain process. Make sure that it only prints everything once. We don't need everything to print. Like if you had 10 GPUs, everything would print 10 times. So that'd be unnecessary. Stick the model into training mode. And now standard training. So for images, targets in train loader. And then we're going to do with accelerator dot accumulate. All right, we're doing gradient accumulation, so we can use their context flag for gradient accumulation. We're going to do the prediction is going to be the loss function. Our prediction is going to be the model, and we're going to pass in our images. Right? Pass our images to the model, no problem there. And then the loss is going to be the loss function, pred targets. Right? We're going to compute the loss between the prediction and their corresponding targets. And that's basically it. As simple as that. This is just cross-entropy loss. And we're hoping that the probability on the channel for that specific channel, for whatever class it is maximized, right? Because there's 150 channels. And so each pixel has 150 values across the channel. So if we remember, it's going to be batch by 150 by height by width. So for each pixel in the height and width dimension, there's 150 values. And we're hoping that whichever value is the correct class label is maximized, right, for that specific pixel. So there we go. That's our loss. And so then we can just store in here our accumulated loss plus equals loss divided by gradient accumulation steps, right? So if we're actually accumulating gradients, so we'll have multiple forward passes, let's go ahead and store in here kind of the average over these steps. Similarly, predicted. So what is our predicted target? So predicted is going to be pred.argmax axis equals 1, right? Along the channel dimension, we want to find which value had the highest probability, because that would be our prediction. And then we can do accuracy is equal to predicted equal targets dot sum. Just add up whatever things were equal. This will make a Boolean. So everything that's equal is true. Adding it together is just adding all the ones together, and everything is 0 is 0. And you divide by torch dot numl predicted, right? So we're just taking the average of how many pixels or how many predictions in our predicted match the ones in the target, added them together, and then divided by the total number of pixels that were in the image. And so that goes ahead and scales it down, averages it out. And so similarly, our accumulated accuracy is, we can do plus equals accuracy divided by gradient accumulation steps, just like that. And so now we need to actually update our model. So we can do accelerator dot backward loss, right? Go ahead and actually compute our loss, compute our gradients, and now we can finally go ahead and complete the kind of the logging and stuff like that. So pretty straightforward. We're gonna do if accelerator dot sync gradients. So just remember, in gradient accumulation is a flag. We only synchronize gradients when the accumulation is completed. Otherwise, it's just inefficient, like it's a waste of compute. So this accelerator dot accumulate is basically toggling this flag, and whenever we've completed our gradient accumulation, then the sync gradient will be true. So when sync gradient is true, that means the accumulation is done, and we can go ahead and do kind of the other things we need to do. So accelerator dot clip grad norm. Go ahead and just do a this is always a good thing to include in model training to make sure none of your gradients are so big that it's kind of ruining your model training or being unstable. So it just clips them. It's especially important at the beginning of training when the model doesn't know anything. And we're going to do loss gathered is going to be accelerator gather for metrics. So remember, everything's happening on multiple GPUs, which means this stuff, right, our accumulated loss and accumulated accuracy is being computed on each GPU individually. So we just need to go ahead and grab them across all the GPUs, gather for metrics, and just average them up to see our overall results across all the GPUs. So accelerator.gather for metrics, accumulated loss. And similarly, our accuracy gathered is going to be, again, accelerator.gather for metrics, accumulated accuracy, right? Just go ahead and store them up. And this will just create a tensor, or basically a list, essentially. It's a list of the loss values, the accumulated loss values, for every single GPU individually. So we're just going to go ahead and average those together, and we're going to store in our train loss.append torch.mean loss gathered dot item. Right? Just go ahead and grab that. So we're going to average up everything across all the GPUs, and then just convert it to a floating point number. Similarly, we're going to store in here in the train acc our average accuracy as well. And so now that we have that, we can go ahead, accumulation's done, so we can go ahead and do accumulated accuracy. Accumulated loss is just 0 and 0, so go ahead and reset them so we can start accumulating and just averaging into them again. And our progress bar dot update 1, right? We've completed one full step, so we can go ahead and update the progress bar. And we can finally do optimizer.step, right? We can actually update our model. optimizer.0grad, and we are good to go. That is our training loop. Similarly, we can do once we've completed training, then we can do our evaluation loop. So that's going to be on, right here. So now we stick the model in evaluation mode, model.eval. And we can do for images, targets, in test loader, right? Test loader. Again, we're going to do with torch.noGrad, right? Because we have no reason to compute gradients when we're evaluating. Pred is equal to model images. And after this, all the other code is the same. So I can go ahead and just copy basically all of this stuff. There's nothing interesting in here, just some logging. So all we're doing is taking the predictions, computing the loss, compute the accuracy, grab the accuracy and the loss from all the GPUs, just like we did before, average them together, and store them in our testing loss and testing accuracy list. Go ahead and just average everything up for this specific epoch, and go ahead and just print it to console. And we are basically done, right? That's basically it. And what we can do at the end is we can do a quick accelerator.save model, right? Save model. We're going to save the model at os.path.join, path to experiment, right? Wherever our experiment is. And we can call this checkpoint f, and we can call it checkpoint epoch, right? Whatever epoch we're currently at, go ahead and just create that checkpoint. It's as simple as that. So nothing really crazy in this training loop. So we can go ahead and just run train and see if it works. If name equals main. I don't think I need to provide any arguments. I think I gave defaults. Yeah, everything has a default. So let's give this a try. So if we do accelerate launch train.py, let's see if this works. Okay, looks like we have a problem here. You need to use even batches when the batch sampler has no batch size. Okay, I've never seen that error before. So, oh, my bad. That should have been batch size, not batch sampler. All right, now let's see. All right, looks like training has begun, but it threw a different error. Just has no attribute parameter. Okay. Did you mean parameters? Parameters. Did I not use parameters? What did I do here? Clip grad norm. I see. Down here. Parameters. Right here. There you go. All right. One more try. Hopefully it works now. Good. So yeah, we can see training has begun. This will be fine. It's already doing distributed training. If we do NV top, you'll see both GPUs are being hit. So we can, things are happening, things are training. Obviously, no one has any interest in watching a training loop, so I'm not even going to bother with this. We'll just kind of look at the results because it's not all that interesting. Let me find the results file. Here we go. All right, so all I did is I went ahead and I just loaded one of my models. I loaded the ADE20K dataset, nothing fancy. All of this stuff here is just to inference our image. So we had to resize the image, normalize it, convert it to a tensor, standard stuff. We grab our image, grab the annotation, we process the image, add a batch dimension, that sort of stuff. We go ahead and predict our model, right? We predict our labels, and then we grab the argmax. We interpolate to the size that we want. That's fine. And then we remember our labels, or the predicted labels, go from 0 to 149. So we have to add 1 to make it go from 1 to 150, just so it matches. I use a color.label to RGB to ensure that the color mapping is the same between the two. And then you can start to see pretty good results, right? Like these are buildings, and so this is the ground truth, and this is our predicted segmentation. And this is another ground truth, this is another predicted segmentation, another ground truth, another predicted segmentation. It's not perfect, right? Like in this case, the ground truth has this as sidewalk and this is road, but we kind of predict everything as road. So it's not perfect, but That's okay. It's always UNet is also not the best architecture for this. That's why we have better models out there like UpperNet, DeepLab, PSPNet, stuff like that. Either way, this was just supposed to be a very kind of long-winded, I guess. We spent, what, almost 2 hours here, hour 45. So yeah, this is basically the end. The main purpose of this really wasn't for segmentation. It's just to give you a feel for the UNet architecture, because we will be just directly using this UNet for the diffusion architecture in the future. The only difference is we need to add 2 different things to the UNet to actually make it work with diffusion. One of them is called temporal embedding, so we'll see that when we do it. It's not all that different. It's actually basically the same as the time embeddings you find in a transformer, and we have to add in attention as well, so standard transformer. So we'll start with this UNet code that we wrote right here. Basically, you can find it in my Git repo in UNet train parts model. We're going to start with this code for the diffusion. This is what we wrote today. We're going to start with this for a diffusion, writing the UNet portion of the diffusion, and then just add in the couple extra modules that we need to actually get it to work with diffusion. So I will see y'all in the next one.